Hello and welcome to Lecture 6, Part C. In this section we will develop the control chart. The control chart allows us to control and monitor a process. It will provide online monitoring to detect changes in a process's quality. We will construct control limits that capture the natural variation of the process. In other words, this common cause variation. We will then collect and plot new measurements against these limits and assess whether there's any unusual patterns. If our process is in control, we would expect that all points should fall between these control limits. We will also be on the lookout for any unusual trends or patterns which would indicate that there is special cause variation in our process. These limits are based on the natural variation of the process. The center line is our X-bar bar, and the upper control limit, UCL, is set at 3 standard deviations above the mean, and the lower control limit, LCL, is set at 3 standard deviations below the mean. We're going to plot a control chart for variable data. This chart is known as the X-bar and R chart. In reality, it consists of 2 charts. One is the chart that tracks changes in our process average or changes in our X-bar. The other chart monitors changes in variability, and this is determined by monitoring the range. Let's take a look at why it's necessary to measure both the mean and variation in a process to understand what's happening. Let's assume we take measurements at 8:30, 9:30 and 10:30. And we're going to take 4 measurements, X1, X2, X3 and X4. And at 8:30, these measurements are 10, 10, 10 and 10. The mean of these is 10. We add them up and divide by 4. At 9:30, we get another 4 measurements, 10, 8, 10 and 12. We add these up and divide by 4, and the mean is 10. At 10:30, we take another 4 measurements, 15, 5, 10 and 10. We add these up and they come to 40. We divide by 4 and we get a mean of 10. Now, looking at this, it would appear that our process is stable. However, if we assess the range and look at the range of our 4 measurements, the difference between the max and the minimum is 0. For 9:30, our maximum is 12 and our minimum is 8, so our range is 4. And at 10:30, our maximum is 15 and our minimum is 5, so our range is 10. So it would appear by looking at the range that the variation is increasing quite significantly, so the process is by no means stable. This explains why we need to measure both the mean and the variation to understand what is happening in a process. The first step in developing the X-bar and R chart is to select the quality characteristic. Next step is to choose the sample size and sampling interval. We will then collect the data, determine trial control limits, and when we're satisfied with these trial control limits, we're going to use these in practice. The first step is to select the quality characteristic. We will be using the X-bar and R chart, so it's based on variable data. So in this case, the data must be measurable. The characteristic that we choose will be a characteristic which affects the process's performance. This could be determined by the critical to quality characteristics. It may also have been identified in the earlier phases of a Six Sigma process, or it may actually be a characteristic responsible for high failure rates. In any case, it's an important characteristic of the process. Our aim is to gather statistics on the process and use these statistics to control the process. So it's important that we choose a sample size. If we're dealing with destructive testing, then we would like the sample size to be low, preferably 1. If the sampling is expensive, we may only choose 2 or 3 parts. The most common number of samples on the X-bar and R chart is 4 or 5. We've identified earlier that the range is extremely suitable for assessing variability when the sample size is reasonably small. How often should we sample? This is often a question. which is very relevant. However, there is no rule. If we're dealing with a new process, or we've made changes to the process, or we're attempting to analyze special causes and root cause problems associated with our process, then we may want to sample reasonably frequently. If, on the other hand, it's a particularly stable process, then we may choose to perform infrequent sampling. Let's choose the example of the pen holder and apply control charts to this pen holder. Critical to quality characteristic was the inner diameter. We're going to take measurements on our process as we are producing these parts and use these to control the production of our pen holders. Let's choose one of these inner diameters. The next step is to gather data on the process. Here we've identified a sample size of 4. So we will take 4 measurements at 8:30. We will take 4 measurements at 9:30, 10:30 and 11:30. So we will assess the mean of the process at 8:30 by means of the X-bar and the variability of the process at 8:30 by calculating the range. The mean in this case is 30 and our range is 30.5 minus 29.5. Maximum minus the minimum. So we have statistics on our process at 8:30. We take another set of measurements at 9:30. We will gather data on our process at hourly intervals and calculate the mean and range at each of these periods. In this way, we plan on getting the average of all those X-bars will become our center line, and the variation, plus and minus 3 standard deviations above and below that, will become our upper control limit and lower control limit. Let's take a look at the data that's gathered over 12 hours. Here we see 4 items being measured. Our sample size is 4. We calculate the mean and range at each of these hourly intervals. Let's calculate the X-bar for this process. We add up all these averages, in other words these X-bars, and divide by 12 because we have 12 subgroups. When we add up all the X-bars, it comes to 362.4. We then divide by the number of subgroups, which is 12, getting a value of 30.2. This becomes the center line, in other words X-bar, the average of the averages. We perform a similar calculation for our range chart. We take the sum of all these ranges and divide by 12. So the sum of all the ranges is 12.3. Dividing by 12 gives us an average range, or R-bar, of 1.025. We now have the center lines for our X-bar and R chart. The next step is to calculate the limits. We have tables of constants to help us calculate the control limits on our control charts. Here we see the equations for our range chart. We see the equation for our X-bar chart. So in order to avoid calculating plus and minus 3 standard deviations, we have these tables of constants that are based on the range. So we look up the value of n, which is the subgroup sample size that we are using, and in our case we're using subgroup sample size of 4. We're taking 4 measurements. So we will use a constant A2 of 0.729, we will use a constant D3 of 0, and a constant D4 of 2.282. These tables of constants are available on the internet or available in any textbook. Here we see the equation for our range chart. The upper control limit for our range chart is equal to D4 times R-bar, where R-bar is the center line of our range chart. In this example, D4 will be 2.282 because we are using a sample size of 4. The lower control limit for our range chart is D3 times R-bar. On the X-bar chart, the upper control limit is X-bar, in other words, the center line for our X-bar chart, plus A2 times R-bar. And we see the value of A2 over here. The lower control limit is X-bar minus A2 times R-bar. When we plot these constants and values for X-bar and R-bar into our equations, we come up with limits on our upper control chart and lower control chart of our X-bar chart. Our upper control chart limit is 37.947 and our lower control limit is 29.453. We can do something similar then on the range chart. Our upper control limit on our range chart is 2.338 and our lower control limit is 0. We will now draw the control chart. We will plot the control chart limits for our X-bar and range chart, including our center line. The top chart is our X-bar chart and the bottom one is our range chart. We will plot our subgroups in relation to these control chart limits. We will plot the X-bars for our subgroups and join them up with straight lines. We will then do the same for our range chart. Here we see our completed control chart. On top we have our X-bar chart and at the bottom we have our range chart. We see the upper and lower control limit on our X-bar chart and we see the upper and lower control limit on our range chart. We then plot the X-bar and R values for each of these subgroups. In total we have 12 subgroups. Let's take subgroup number 4. In subgroup number 4 that we took at 11:30, we had a measurement of 30.9 on our X-bar and 0.9 for our range chart. Here we see 30.9, very close to our upper control limit, and we see just below the center line at 0.9. We similarly plot the X-bar and R values for the remaining subgroups. This concludes part C, where we develop the control chart.